Hello learners, welcome to session 5 for 3 Algebra of Numbers. In this course, I am Unkaila Dasmani and I am your course instructor. In this session 5, we are looking at prime numbers. A natural number p which is not equal to 1 is called a prime if its only divisors are 1 and p. I think you completely agree with me. If a natural number n which is not equal to 1 is not a prime, then what do you call it? Then we say it's a composite number. So 2 and 3 are prime numbers, while 4 is a composite number. So this section is very interesting. Let's look at more about prime numbers. Session objective. By the end of this section, you should be able to give examples of prime numbers. You should be able to explain prime factorization, determine the LCM and GCD of sets of numbers. Should we also prove the theorems involving prime numbers by contradiction? Okay, definition. Prime numbers serve as the basic building blocks in the multiplicative structure of integers. This is according to Algebra 1975. So Algebra observed that there are two facts about the distribution of prime numbers. The first is that they are the most arbitrary and unary objects studied by mathematicians. They rule like weeds among natural numbers, seemingly to obey no other law than that of chance, and nobody can predict where the next one will sprout. So the second fact is even more astonishing, for it states just that the opposite, that is, the prime numbers exhibit stunning regularity, that there are laws governing their behavior, and that they obey these laws with almost military precision. So that is very interesting about prime numbers, thanks to Algebra. So the definition. Let p be an integer such that p is greater than 1. We say that p is a prime number, or simply p is prime if the only positive numbers that divide p are 1 and p itself. Any integer n greater than 1 that is not prime is called composite or composite number. So that's the condition for a number to be a prime: when the number divides itself and then the factors are 1 and the number itself. Okay, great. Next slide. Theorem. There exists an infinite number of primes. You have infinite number of primes, it's uncountable. You cannot finish counting the prime numbers we have. And this is just simple and so simple proofs. And this proof is just called contradiction. By contradiction, assuming the negation of desired results and working towards two mathematical statements that contradict each other. So this is just simple and go through. Okay, let's look at an example. Determine if each integer is prime. If not, state the possible integer divisors of the given number. So I jump over that. Just a primary work, just too basic. So you can go through. Now, primes and irreducibility. Let p be a member of Z and suppose that p is not 0 and not a unit. Then 1. P is said to be irreducible if whenever p equals ab, then either a or b is units. Yes. So either a or b is units, then we say that p is irreducible. P is said to be prime if whenever p divides ab, then p divides a or p divides b, then we say that p is prime. It will show that the notions of primes and irreducibility coincide for the integers. Okay, let's look at theorem and then the proof. Let p be a member of Z, then p is irreducible. So how do you prove? I think the proof is just like ABCD. Suppose that P is prime and P equals AB. Once P is a prime, definitely P can be written as AB. Then P divides AB, so either P divides A or P divides B from the theorem, which we agree to that. Once P divides AB, then P will divide A or P divides B. Suppose that P divides A, then P will be equals AX for some X, and you agree to that. And that P will be equals to PXB, which you agree to that, because what do? You put A into the here from here. Let me call this equation 1. So here from equation 1, we put A here into equation 1, we get PXB. Okay, and that is true. Let me call equation 2. So it follows that we can bring Px to the other side of the equation, then you factor P out. So you get P brackets open 1 minus x equals to 0. Since P is not equal to 0, we must have x minus b, x minus xb equals to 1. That is, once P is not equal to 0, 1 minus bx must be equal to 0. And if 1 minus bx equals to 0, that is 1 minus bx equals to 0. From that, we can have xb equals to 1. xb equals to 1. Okay, so b is a unit, because xb equals to 1 is a unit. Similarly, if p divides b, then we can now show that a is also a unit. It follows that p is irreducible. P is irreducible, and that is true to the proof. Another theorem, let P be irreducible and A be a member of Z, then either the GCD of PA equals 1 or P divides A. This proof is just simple like ABCD. So go through and read, because we have a lot of other things to consider. Suppose that P is irreducible, then P is prime. As a consequence, we have P is prime if and only if P is irreducible. So similar like the other theorem. So we try to go through. Division algorithm. Division algorithm. Suppose A and B are integers with B not equal to 0. This algorithm computes integers Q and R such that we have the interval A will be equals to B Q plus R. Don't forget about your remainder. We use the definition algorithm repeatedly to compute GCD of set of numbers. So we want to compute GCD of set of numbers, and this will guide us to do that. Example 19. Let's compute the GCD of 2261 and 1275. So we are using the division algorithm approach. So by using the division algorithm approach, we can now compute the GCD of 2261 and then 1275. Okay, so how do you compute? Let's start with the 2261 being the higher number. 2261 will be equal to, you can see that is same as 1275 times 1 plus 986. And then what's happened next? You can also say that the 1275 equals 986 times 1 plus 289. Good. And then you can also see that the 986 is equal to 289 times 3 plus 119. Okay, so what's happening? You can also see that 289 will be equals to 119. You multiply by the 2, that's times 2, times 2, times 2. Okay, plus what will be the remainder? 51. Okay, and then 119 also equals to 51 times 2, and then the remainder is actually 17, and that is the division algorithm. And then we can now write 51 is equals to 17 times 3. 17 times 3. Okay, so having reached here, therefore we can conclude that GCD of 261 and then 1275 equals to 17, and the reason is that 17 divides 51. 17 divides 51, so the GCD is actually equal to 17, and that is great. Let's also look at the next example. Similarly, using the division algorithm, we can also find the GCD of 437 and 323. So here we start with the one with the bigger one, that's 437. 437 will be equal to 323 times 1 plus 114. That will be the remainder. This is actually plus, this is plus in mechanics. So plus. Then we can also say that 323 is equal to the 114 is going to eat 2, remainder 95, and then 114 will be equal to 95 shows 114, where you will get 1, so 95, 1, remainder 19, good. And then 95 is equal to 19 shows 95, 19 divides 95, we get 5, so 19, 5, and the remainder is actually 0, and this one you may ignore to write it. Therefore, because 19 divides 95 and the remainder is 0, we can say that the GCD is the 19 here. The GCD is the 19. This 19. Okay. So we have our 19 to get GCD. Therefore, GCD of 437 and then 323 equals to 19. Thank you. And the reason is that 19 divides 95, which is 95, and so keep on, and that is the division algorithm approach.